Yes, so okay, as usual, we'll wait for a few minutes before starting. Okay. Since there are three of you, I'll start. So again, we'll continue with estimation. So what we derived last time was that sorry about this. This screen is misbehaving. So if we have this okay. We have samples from Gaussian random variable and such that the then we had derived that mu hat equals minus. Fine. And that Fine. So this estimate is this is biased. Fine. So now the question is how to make this estimate unbiased. The answer is that make sigma hat square biased, or rather there exists constant minus n by n. For a given n, this is a constant, rather n over n minus 1, such that, just a second. Yes. Such that value of becomes. So now we can simply multiply the estimate with a constant and make it unbiased. So making a bias estimate unbiased is quite simple in some cases, but nonetheless we need to be careful that whether the estimate is unbiased or not. The next thing is that let's now consider another thing, that is, so this is about the bias of an estimate, that we desire an unbiased, and if we biased estimate to make it unbiased. Fine. Somehow my laptop touch is misbehaving today for some reason. I don't know why. Let me correct that. So the next thing to consider over here is after we are done with the bias, apart from the bias, we also have something that is called the variance. Let x hat, or rather, let theta hat be an estimate of theta, then the variance of theta hat is value of theta hat minus theta whole squared. So see, this is not the variance of a random variable. This is the variance of the estimate, which is the true value minus the which is the estimated value minus the true value. So this is how we define the variance of the estimate. And since the estimate is a random variable, we would want minimum variance estimate. Now, however, so we therefore want the I don't know why this is misbehaving today. The variance unbiased estimate. Now we ask the question, isn't with the unbiased estimate be minimum variance? Let's try to answer this. Consider x to be, or rather xk to be having a mean a and a variance sigma square, with a being stick and unknown. And now put this thing. with A being deterministic and unknown. And now consider n samples of xk, x1 to x capital N, and consider bias estimate. Consider the biased estimate A hat equal to alpha by n now. So want not an estimate, but expected value of equals square square minus, oh sorry, alpha square by n square minus alpha by n, f2 alpha by n, k summation k equal to 1 to n xk plus a square equals square by n square now. This we already know is n square mu square plus, rather skip a step, and alpha square times a square plus minus 2 alpha a square plus a square. Fine. So variance of a hat equals alpha square sigma square by n alpha a square k square. Now for minimum variance. So now this variance actually variance of A hat is actually function of alpha and n minus. Therefore, this and we can write twice alpha. Hmm? Just a second. Yeah. Yes. So this becomes twice of alpha plus sigma square by n minus a square equal to 0, or alpha equal to a by a square plus sigma square n. Fine. So this and so the alpha and but for unbiased estimate alpha equal to 1, so the minimum variance solution is not unbiased and vice versa. This is the first takeaway. 2, as n tends to infinity, so with an infinite number of samples, we can say that the unbiased estimate is also the minimum variance estimate, but other than that, the minimum variance estimate and the unbiased estimate are two different things. So the question is that what do we want now? That do we want the unbiased estimate, or do we want the minimum variance estimate? And as always, there is no one given fixed answer to this. So this is called that we don't want bias, but we want as little variation in the estimate as possible. So because as you might notice that the variance of the estimate essentially an indication of the error power that indication of how much estimate can different from the true value. So therefore, we are in a dilemma of what is known as the bias variance. The bias variance. Just a second. Yes. We have what is known as the bias variance dilemma. That is, or the bias variance trade, which essentially means that with a fixed number samples, you can either have a minimum variance estimate or can have an unbiased estimate. You cannot have both. So it's upon you to choose whether you want a minimum variance estimate or an unbiased estimate. So I shared a Wikipedia article that was called bias variance trade-off. You can have a look at that. Just add that to the notes. I don't know, my laptop is hasn't misbehaved in 2 years, and today it's grossly misbehaving. Oh, Excellent. The pen batteries have died. It's working. So the bias variance trade-off. So it seems that the pen batteries have died. So what? Just give me another minute with this. Yes. So yes, the battery of the pen is dead, and oh, it's working again. So let's see if it still works. What I was about to say that yes. So now it's working again. So there's a shared Wikipedia article on the group that you can look at. Then after we so what we look for is actually therefore what we look for is the unbiased estimate that has the minimum possible variance. So in general, define the minimum variance unbiased estimate biased estimate that has the minimum variance out of all possible estimates. Fine. So we define the MVU estimate as the unbiased estimate that has the minimum variance out of all unbiased estimates. As an example, again, we have x1, xn. Again, a DC level in, we want to estimate a DC level in noise. Now, the question is A hat equals x1 So the question is this an unbiased estimate? So answers. Anyone? Is this an unbiased estimate? Yeah, Aditya.
No, sir. It can be an unbiased.
Louder.
I don't think it's an unbiased system.
Okay, so what is the condition for an unbiased estimate? The condition for an unbiased estimate is that expectation of A hat should be equal to A.
Yeah.
So expectation of xk equals A.
Right.
Right? So this is unbiased. Fine?
But I don't think it's minimum variance.
Yes, exactly. This is an unbiased estimate. We are just talking about an unbiased estimate. Okay. So xk is an unbiased estimate with variance sigma square. Fine. Now A hat, or let's say instead of A hat, let me call this A hat prime equals half xk plus xl, k not equal to L, and Aditya, you have forgotten to turn off your mic. Thank you. Yes. So this is also unbiased. Variance is sigma square divided by 2 for we average any L out of samples, we get unbiased estimate with a variance 1 by, sorry, fine, sorry, sigma square by L. And how you say that you take a weighted average, give weight alpha 1 to the first sample, alpha 2 to the second sample, such that the sum of all alphas equals 1. That would also be an unbiased estimate of A, right? So in that case as well, so you'll get some variance. However, the variance of all the possible unbiased estimates is minimized when alpha 1 equal, or when all the equals are considered together and given equal weights. And this is the for this given case. So in general, we want to find the minimum variance unbiased estimate for any parameter. So however, there is no. So for the average, you know how to find the minimum variance unbiased estimate. Even for the variance of a Gaussian random variable, you can try to find the minimum variance unbiased estimate. But the problem is that exists no standard recipe for finding bias or finding the minimum variance unbiased estimate. What you have is that instead exists theorem that says that if at all minimum variance unbiased estimate exists, then the or rather I cannot go below the so there exists no standard recipe for finding the minimum variance unbiased estimate of a quantity. Instead, there exists a theorem that says that if at all minimum variance unbiased estimate exists, its variance is no lower than the Kramer-Rao lower bound, and the Kramer-Rao lower bound is the minimum variance that that estimate can achieve, or that an estimate can achieve, or the CRLB. So minimum variance that an fine. So this. So this is the Kramer-Rao lower bound. So if you have questions regarding this or till this point, now is a good time to ask them. If you want me to go back to a certain point in the lecture, I can do that as well. But if you have questions, now is a good time to ask them. So, no questions. That's good. I'll just check the chat as well. So, okay. No questions. This is a good thing. So, or not necessarily a good thing. Either you are understanding everything or you are understanding nothing. Anyway, so coming to the Kramer-Rao lower bound. So the official statement, we'll first state the theorem for a scalar case and then extend it to a vector case possibly in the next class. So yes. So theorem. Assuming that the PDF theta for a single scalar theta satisfies satisfies the condition del by del x will 0, then the variance of any unbiased estimator theta hat of theta must satisfy the lower bound given as variance of theta hat greater than or equal to 1 upon I theta, where I theta equals minus of expectation of del square natural log of p or px given theta. Or minus expectation of del square L theta by del theta square. I theta is called the Fisher information. Moreover, if can be reduced from then optimal fine. So, and there's a natural extension to a vector parameter that for a vector meter theta hat, the vector parameter theta is covariance of theta hat is means covariance of theta hat minus theta is positive semi-definite. So this is a positive semi-definite matrix with I theta equal minus of expectation of del square L del square L theta where I of theta called the Fisher information matrix for the vector theta. Now again. Estimate is possible if del L theta can be written as I theta G theta Gx minus theta. Fine. So, or you can say that if theta, if it can be written in this form, if I inverse theta of the first derivative of L theta can be written in this form, then you can find an optimal estimator. So we will not prove the Kramer-Rao lower bound. We'll just state it. So I think now is a good time to stop. If you have any doubts, we can talk about them.
Sir,
Yes, just a second. Yeah, tell me.
sir, so there was this theorem, right? Um,
Sorry,
there's this theorem which is called Layman theorem.
this does this theorem what, Aditya?
Yeah, the Layman theorem, something Layman Swift theorem, something like that.
No, I haven't heard of that.
Yeah,
So
so
maybe you can type, you can ask, you can type the name properly in the uh, post box and we can discuss it over chat. Sounds good? Aditya, so your voice is breaking.
I said yeah. Uh,
Okay, great. Anyone, anything else? Okay, so then we'll hang up and I'll upload everything as usual and we'll talk on Wednesday. Okay, bye. Have a nice day.